In this PhysCast, we're going to calculate the expectation values of momentum and momentum squared for a particular wave function. This follows on from a previous PhysCast where we used the same wave function but calculated expectation values related to position. So it would be very useful if you watch that previous PhysCast first, as we'll be using some of the results for that in this particular calculation. One of the things we need to do when we're calculating expectation values is to make sure our wave function is normalized. And we did that in the previous PhysCast, and we calculated that the value that this a constant must be to normalize this wave function was indeed 2b over pi all raised to the power of 1/4. And you might want to go back to that previous PhysCast and make sure that makes sense. But if we do have a normalized wave function here, to calculate the expectation value of momentum, what we need to calculate is this integral over all space, so from minus infinity to plus infinity, of the complex conjugate of our wave function, psi star, the thing we're calculating, in this case momentum, and the wave function psi there, again integrating over all space. When we're doing quantum mechanics, it turns out we can't really write down momentum here as some function of position that we can then integrate. So instead, we think about this p times psi here as an operator p acting on the wave function psi. And the operator that corresponds to momentum is minus I h bar d by dx, this kind of derivative operator here, acting upon psi. And that's how we have to think about this calculation here. P is not just some functional form we can put in there. P is an operator that acts upon the wave function, and that's why it's important when we're doing these expectation value calculations that we stick to this ordering inside the integral of psi star, the thing we're trying to calculate, and then psi. Otherwise we might have this operator acting incorrectly. And we can actually calculate what this will be for this particular problem here. We're going to want d by dx of our wave function here, which is capital A e to the minus bx squared minus I omega t. So to take that derivative, you can see minus I h bar at the front here. We're going to bring down, well, the a will remain, the a is just a constant. We're going to bring down the derivative of what was in the exponent. In this case, that will be minus 2bx, and then we leave the exponential essentially unchanged, minus I omega t. And we can simplify this a little bit here. We're going to have 2I h bar a x e to the minus bx squared minus I omega t. That's what we write when we write down the momentum operator p acting on the wave function psi. And so we can put that back into our calculation here for the expectation value. So pulling some constants out the front here, we're going to have 2I h bar. Now we'll also get a factor of a from psi star in here, so we'll actually have a squared out the front here. And then we'll do the integral from minus infinity to infinity. And when we did the psi star times psi, as well as this a squared, we had to do this exponential multiplied by the other exponential with a different value for the I in there. And as you saw in the previous PhysCast, we wind up here with x e to the minus 2bx squared is the integral that we need to do. It's useful in such integrations where we're going symmetrically about the origin to check the symmetry of the thing we're integrating. And this function here, you should see, is an even function. It only involves x squared. And this factor here is an odd function. It will certainly reverse sign compared to on the right hand side of the origin to the left hand side of the origin. So an odd function times an even function will give us an odd function. That means basically as we integrate this on the negative side, we'll get exactly the same value but opposite sign to when we integrate on the positive side. All of that resulting in this integral being exactly 0. So our expectation value for momentum for this wave function here is exactly 0. Let's just write that down up here perhaps. And there are similar symmetry reasons why you might expect this for this type of wave function, as we saw in the previous calculation for the position expectation value, namely that this particle described by this wave function is equally likely to have a positive or negative momentum. Remember, momentum here is a vector quantity, and therefore when you think about the expectation value averaging over the measurements you would make on a large number of identical systems, then those quantities would all average out to 0. Let's now think about the calculation we do to find the expectation value of the square of momentum. So similar notation, we're looking at the expectation value of p squared. So the thing in our integral here is p squared, and we need to think about how we put p squared into this kind of calculation. So one way to think about p squared here is we can think about it as the operator p acting on the operator p acting upon the wave function. And if you like, that can of course be minus I h bar d by dx acting upon minus I h bar d by dx of the wave function. That's what we're doing when we're doing p squared here. And if you go back and look at the previous calculation we did, we've already done p acting on the wave function. We really want here minus I h bar d by dx of that thing we had in our previous calculation, which, if you remember, was this 2I h bar a times bx e to the minus bx squared minus I omega t. And once more, we can pull out all of these factors that are constants out the front. I times minus I will just give us 1, and so we'll wind up here with 2 times h bar squared times a times b, and then we're going to want to take the derivative of things that do involve x, which will be x e to the minus bx squared minus I omega t. And then we need to make sure we remember our product rule here for differentiating something here that has two factors that depend upon x. So we'll leave our 2 h bar squared a b out there. So let's differentiate that first term. The first factor just gives us 1, and then we leave the second factor alone, e to the minus bx squared minus I omega t, and then we'll leave the x alone, and we'll take the derivative of this exponential, which, if you recall, gives us minus 2b times x, and that'll give us an x squared there because we already had a factor of x, and then we'll end up with e to the minus bx squared minus I omega t. And just to simplify that a little bit further, we can actually pull out that factor of the exponential because it's common, so let's get 2 h bar squared a b e to the minus bx squared minus I omega t all into 1 minus 2bx squared. So that's what we got when we've got p squared acting on our wave function. And that's what we're going to want to put back up here into our calculation. So once more, making sure we keep track of all of our constants, we're going to be having here 2 h bar squared. Again, we'll pick up another factor of a when we put in the psi star, so we'll get a squared there and b there, and then we'll be doing an integral here from minus infinity to infinity of this e to the minus 2bx squared. And remember that I omega t term will again cancel out when we're using the complex conjugation to multiply through into this 1 minus 2bx squared dx. So we essentially have two integrals to do here. We'll just write them out again to see that there's two separate calculations we can do. So there we have that. And just make sure you keep careful track there. We ended up with a b squared term in this second integral here because there was a b in there. And one thing that would be useful if you have watched that previous PhysCast where we calculated the expectation values of position is one of these integrals is exactly the same as we've already seen before. This particular integration here from minus infinity to infinity of x squared e to the minus 2bx squared. So that one we actually already have evaluated, and if you're not quite sure some ways of getting to the answer to that, you might want to go back and look at that previous PhysCast, or of course you might just look up this as a standard integral that you might have available to you either online or in a book somewhere. But either way, this thing comes out to be the square root of pi divided by 4 into 2b to the power of 3/2. Now going back to this first integral here, again it's useful to look at the symmetry of what's happening in our integration here. We're integrating from minus infinity to plus infinity, and we can see that this function in here is actually an even function. It only depends upon x squared. So one simple thing we might start doing is to say, instead of going from minus infinity to plus infinity, we can simply do twice the integral from 0 to infinity of this same even function here, e to the minus 2bx squared dx. And then you might look up this as a standard integral. And if you did that, what you would find for that integral there is you'd end up with the square root of pi on 2 times the square root of 2 times b. and not forgetting you've got a 2 out the front here because you took into account that it was an even integral, so that 2 will actually cancel with that 2 at the front there. And so what you're left with this integral here is root pi over root 2b. Now we need to put all this together, keeping careful track that we don't drop anything in our algebra along the way. So we'll wind up here with this 2h bar squared a squared b multiplied by root pi over root 2b, and over here we'll have this minus 4h bar squared a squared b squared multiplied by root pi over 4 times 2b to the 3 halves. And there's a lot of terms here to keep track of, and there's some fairly straightforward cancellations you can see, and you might want to go back once more and check that previous PhysCast to see some straightforward ways of collecting all of the right terms here, but you should end up with something to do with h bar squared and also to do with capital A squared still, and you can go through and show what you're left with in terms of, say for example, pi and b, and what you'll wind up with here, if you do it correctly, is the square root of pi times b divided by 2. And then we can actually use our expression that we know for this normalization constant, a squared, and we find we'll have h bar squared. Now a squared here will be root 2b over root pi, because we're going to be squaring that thing that was raised to a power of a quarter, and we can then multiply that, as we've seen here, by the square root of pi b over the square root of 2. And we're going to get some nice cancellations here. The root pi's cancel, the root 2's cancel, and we're going to get root b times root b, which just gives us b, and our final answer here turns out to be h bar squared multiplied by b. That's actually the expectation value of the square of the momentum for this particular state. So let's write that up again here. The expectation value of p squared turns out to be h bar squared times b. We should finish with checking whether these things make sense. I already mentioned we have some good symmetry reasons to understand why the expectation value of momentum came out to be 0. What about this expectation value of p squared? Is this a reasonable thing to have come up with? One thing we might check is that the units make sense. So what are the units of a momentum squared? The units of a momentum squared will be the units of momentum, which you should remember are kilograms meters per second squared. Now what about the units of h bar squared times b? Well, the units of h bar squared times b will equal, well, let's just think about what h bar is. H bar is Planck's constant on 2 pi, and Planck's constant has units of joules times seconds. So that will be h bar squared. And b, you might have to go back to the previous PhysCast once more to see what we figured out the units of b must be, and they were going to be units of inverse length squared, so say meters to the minus 2. We'll need to maybe expand a bit on what we understand a joule to be. A joule, you might recall, is a kilogram meter per second squared, sorry, meter squared per second squared. Go back and double check that. And we're multiplying that by a second to get a joule second. That's all squared multiplied by this inverse square meter from our units of b. And we can see here, hopefully, some collecting of terms in here. We're going to have a kilogram, let's say kilogram squared, meter to the 4th, let's say second to the minus 1 squared is second to the minus 2, and then we're going to multiply all of that by this meters to the minus 2, which should give us kilogram squared. Meters actually come out to be squared, so meters to the 4th, meters to the minus 2, and we're going to get seconds to the minus 2, which is indeed a kilogram meter per second all squared, which is what we wanted. So the units check out. The last thing to think about is the behavior. As b gets larger here, as this value b in our wave function was to get larger, then our expectation value of p squared would get larger. And you might recall from the previous PhysCast that we said this kind of Gaussian shape here, the width of this goes inversely with this value b. So if b gets very, very large, we're getting to be a very, very narrow Gaussian distribution, and that means it's going to be far more particle-like. It's going to have a much better defined position, and we know from our understanding of the uncertainty principle, for example, that as its uncertainty in position gets smaller and smaller, its uncertainty in momentum must get larger, and that's kind of reflected here in that this expectation value of p squared is going to get larger the narrower this distribution becomes.